Hey, folks, we're in a hurry. We were parked up on the side of the road and a Dakota pickup truck pulled up next to us. And some folks got out, they had backpacks that looked a little semi-official. And we talked to them and they said they were geologists from a local university who are on the lookout for a fault line here in the Upper Peninsula. We're probably 5 miles from Joyce, Washington. They've had to leave right away. And so they said they're going to leave a marker for us on the road here to show us which way they went. And they're going to tell us a little about what they do. So, hey, follow us.
So my name's Liz Schermer, and I'm a geology professor at Western Washington University. And I've been there for more than 25 years, and my specialty is tectonics, so faulting at the surface all the way down to the depths of the crust.
One of the things they showed us was a map basically showing a stream bed that had been displaced, showing that at some time in the past there had been an earthquake here. We'll find out more as we continue.
And Cody is a new master's student. He comes from Colorado College, and we're excited to work with him on this project.
We're not sure how far up the road, maybe a quarter mile, so we're in a hurry to kind of catch up. We're not sure what kind of marker it's going to be. We could miss the whole thing entirely, but they did say wear long pants and be prepared for bushwhacking.
And Cody, why did you pick Bellingham, Western Washington?
Well, I would say the main reason would be to work with Liz and another professor, Colin Amos, who's also there.
This spot here is less than maybe 50 meters from where we parked. Now, it's entirely possible this was the trail they took, because coming around this corner they could have disappeared this way, but it's way too close. Meanwhile, I don't see any kind of marker here.
Neither do I.
But let's take a little walk up there anyway and see where, when it's dead end.
So how did you hear about Liz?
Well, I did know some people who went there and reached out to both Colin and Liz to see what kind of projects they had in the works, and I came and visited, and they showed me the LIDAR and other, showed me different aspects of the project, and it was really interesting to me. So, yeah, that's what I wanted to spend the next 2 years doing.
Well, I guess this last conjecture was correct. There's our cairn, consisting of 3 stones with a stick marking a direction onto a trail that I would definitely describe as being a bushwhacking trail. Let's follow it. Cody, a professor there, tells me this is your master's project.
That's correct, yeah.
And it's enabled by a certain technology that's now available from space. It's called LIDAR?
LIDAR, it's not, well, it's from planes actually.
Oh, it's
airborne LIDAR. Yeah.
Heading into a bit of a deep wood. Down below, clearly a gorge for some water flow, although I'm not hearing very much flowing at this point in soil.
Laser.
Yeah,
They use laser.
Not radar.
That
Wow.
pulses down and hits the treetops, so foresters use it for forestry studies. And then they can do some math and figure out, okay, like if the plane's up here shooting this laser down, the first return comes from the treetop, and then there's a bunch of things that hit parts of the trees, and the last return comes from the ground.
Oh, so they can measure
strip
the
it all
return time to such precision that they can strip away layers from the canopy all the way down to the ground.
Exactly.
Wow.
So you can essentially just remove all the vegetation, only see the topography.
So they call these maps that we're working with bare earth LIDAR.
Right.
You can see this trail isn't entirely unmaintained. Obviously, somebody split this log to continue the trail between them.
In this area, the DNR flew it because for forestry reasons, and they fly it for stream habitat reasons and that sort of thing.
Oh, so they commission these and then...
Commission it, but then it goes into something called the Puget Sound LIDAR Consortium, which is an open data.
Yeah, so you can go online.
You can go online and see it.
Yeah.
Washington LIDAR portal, if you look at it.
Yeah.
I've been walking this trail for at least 10 minutes now, not hearing any water flow. I'm also looking for any signs that there might be another cairn. The cairn marker is usually stone, and I don't see much stone along here. And so your project is going to be to investigate previously unrecognized fault slippages and displacements.
Pretty much.
Pretty
yeah.
much.
And I just started. Like this is my first week of
Real investigation.
school, even.
Yeah,
too,
he's not actually officially a student yet.
Yeah, I haven't
No
taken any
kidding.
classes
He's
yet.
an overachiever.
Yeah.
Wow.
I'm just here early.
Wow. I imagine if I were any good at tracking, I'd be able to notice some kind of commotion. Broken fern leaves, trampled on fern leaves, broken twigs, maybe even footprints to indicate a recent passage. So how'd you hook the professor into this?
She hooked me into it.
No kidding. Because you said something about this as a project you had started yourself a while ago.
With my USGS colleagues, and we actually just published a paper that kind of did a preliminary study of this LIDAR, but nobody had been on the ground. So we're like, well, we better see ground truth.
One of the things I've noticed in my own life, and you probably know it too, is that it's a whole lot easier to discover something than it is to find it.
So it's called the Lake Creek Boundary Creek Fault. So Port Angeles is here, Lake Crescent's there, and 10 years ago we worked on this section of it and discovered there were earthquakes. And then more recent, this section is not exposed. And then more recently we're actually on this section right here, right now.
What plate is this on?
This is all the North American
All the
plate.
North
So
American
the plate boundary with the Juan de Fuca plate is way out here.
Oh,
Let's see
okay.
if that might be in this picture. No, yeah.
Oh, I see. Here
So
we go.
here's our square, and there's the plate boundary.
Just come up that trail to emerge on a gravel road. And frankly, if there's a gravel road here, it would have made a lot more sense just to have driven up here. So clearly, I am not going to be able to turn these folks up.
Do they run different directions?
They do, yeah. So this plate boundary runs this way.
North-south.
And then there's lots of faults in, well, you can see on this map, all these faults like this, and so there's lots of faults in the North American plate that probably get stressed by the subduction zone.
I do believe this is the trail I came in on, and I noticed this little stick branch pointing off to the right. Well, I suspect they left this here so that they could find the trail as well as guide me and them back to the trail they came in on.
But they also get stressed by California running into Oregon, Oregon running into Washington, and British Columbia.
Don't they have like any
Not
traffic
moving.
rules for these things?
British Columbia is sort
Yeah.
of, it's the buttress, it's the traffic jam, and so everything's crunching up against British Columbia.
Now, of course, as I proceed back the way I came, I'm also having to make a gentle climb. Heart rate, breathing, and perspiration are all in the ascendant. We've got a tough question for you. Have you ever heard of the Mima Mounds?
I have.
Now,
haven't, no.
any idea what caused those, the regularity and the size and the location of the mounds down
it's-
near Olympia, Washington,
Yeah,
Capitol
Olympia, and
Forest?
there's some out near Ellensburg or Yakima. Yeah,
Giant moles?
that's one idea, is that it's animals. I mean, nobody has actually been able to prove. Some people think it might be seismic shaking.
Uh-huh.
Some people might think
So that would be a resonance pattern.
Yeah. Some people might think it might be some sort of what they call periglacial, like on kind of like frost patterning.
Sure.
You know how frost kind of makes polygons or whatever, but for some reason these are mounds.
Trail's beginning to open up now. It's pretty clear that soon I'll be on the unimproved wheeled lane I originally descended off of once I discovered the cairn. Okay, I'm about to disassemble this cairn so that they'll know that I actually did find this point on the return, as well as that log I left back at the other, what I suppose to be the other marker. It's about 8 p.m. I'm sitting alongside Joyce Road in the Upper Peninsula of Washington State. I'm waiting for our intrepid pair of geologists, one budding and one a professor, to return from their inspection of a displacement fault that occurred along a local stream. Wow, we have a visitor. Look, some kind of mole. Hello, Mr. Mole.
He's not shy, is he?
Oh, look at that. It's now 8:15. It's on Thursday, July 20th. Actually an anniversary of the first Apollo mission to land on the moon in 1969. I'm doing my second synchronicity zoom, hoping by the time I reach the zoom potential of this camera, that our much awaited for geologists will emerge from the shadows. On the off chance that I might encounter our investigators, I've headed on down the trail. Before it gets too dark, perhaps, perchance, to encounter them. And there they are! Zowie!
Sorry, we kind of ditched you.
No, that was great.
It was all for the better because it was a horrible, horrible bushwhacking.
Yeah.
Oh, well, no, I actually got all the way down to that gravel road. I found your cairn. I walked along that escarpment, which dumped down towards the river.
Oh yeah, see, we cut up the road. We didn't go all the way to the
I was
gravel.
wondering why.
We kind of waited in a bunch of places thinking you might come see us.
Well, that was really sweet that you guys were willing to take some time off from your investigation. What did you find?
Well, we didn't get to where we wanted to go.
Oh.
It was the
field
bush-
work, right?
The bushwhacking got worse and worse and worse.
Did you notice the gravel road way down there?
Yeah, I've been on that road before.
And that did not lead down to where you were
No,
going.
because we had to go up the hill.
Yeah.
Yeah. So we got probably a quarter mile from where we needed to go, and we decided it was too hard going. We needed to turn around.
Yeah.
But on the way back, we found some good glacial deposits.
Oh, well, and who identified those deposits? The student or the teacher?
We both kind of did.
Very good. It must be great to go out and do a little bit of field work.
Yeah.
If you want to come with us tomorrow, we can meet you somewhere.
Where are you going next?
We're going to go a little bit further west.
Uh-huh.
We actually are going to go through a locked gate, but we could let you through there and go see where, in a clear cut, where it's more obvious that
Displacement has occurred.
yeah.
So you guys are strictly looking into fault line displacement here in the peninsula.
right. But we
Right.
need to know what deposits are displaced. That's so knowing
Right.
whether it's
Oh.
glacial or younger than glacial is important.
And they'll give you an idea of when the actual earthquake occurred.
Exactly.
Oh, very cool. So Liz and Cody are about to head off to their campground for the night, and we've been invited to participate in more of their studies tomorrow if we can work out the logistics. And you can see that Cody's explaining some of the intricacies of deformations and
Well, I'm
quake
just giving
zones and everything else
So
to
like,
Vanessa
if
over
we
there.
if we looked at them afterwards,
Best way to learn is to
and see how
teach.
often they occur, we could
Why don't you give me
See,
your
right.
card?
We're at the Lyre River Campground, and here comes
Cody and Liz.
Cody and Liz.
We're about to follow them out to a geological inspection site where we should actually get some indication of earthquake displacement. Not sure how far we're going. We're going somewhere where they have a gate. These guys have the key, and then we're going to go in and take a look at some different formations.
We're turning onto Highway 112.
West, Upper Peninsula, Washington State. We're taking a left. This could be the area with the gate that Liz has the key for. However, she said there's a lot of trucking activity here today, and it would appear as though their comings and goings are leaving the gate open. So we may not actually have to fish out the key.
Washington Green. On today's the 21st of July.
Friday is
This road is closed to off-road vehicles even.
And
These are old logging roads.
foxglove. Something like it anyway. Beautiful.
Part of Washington we wouldn't get to see.
Generally, we would avoid having to travel on roads like this, frankly. We don't have your ground clearance. Sorry about putting an anchor on you a little bit. We get.
Another mile or so, and then we'll stop.
Okay, that sounds good. And it's about pretty much like this.
Yeah, the road never gets any worse.
Oh, well, I think we can handle it.
So we wouldn't know what the significance of this swamp was unless we had this LIDAR. But it's common when you're looking for faults to find drainages that have been dammed by earthquakes. So when the ground goes up, it dams the stream and creates a swamp.
So ordinarily, you wouldn't expect to find a swamp out here. Except for the
Right.
displacement of the land that
Right.
created a back flooding.
Exactly. Yeah. Exactly.
And so, however, with you might have suspected there was some kind of a fault declivity here, just because there was a swamp. But when you got the LIDAR images, you knew for sure there was
Right.
one here.
Right.
Wow,
Exactly.
I get
So
it.
you can see. Well, this isn't this place, but it's more obvious here. Here, a stream comes out into a bigger valley, and here's the scarp. So that when that land goes up, it blocks that stream and creates a swamp down here. This place here is a little bit less obvious on the map because I don't have.
You don't have
Where are we? Are we? I think it's not on this.
You can
exact
see on
spot
this
here.
one, so
Yeah.
we're more or less right here. And this swampy, that's not entirely right. We're like where that purple pin is. And
We're moving around apparently.
Yeah.
Oh, the satellite is.
Yeah. And so that would be the
So yeah,
slope
so
there.
see these creeks that come down this way. So the ground is sloping this way. So you expect it.
Ordinarily, they would connect right up with this
Right.
other side, but
Yeah.
they're broken up. So all
Exactly.
of this was just basically blocked up. Wow.
Exactly.
Go ahead and
Gotta
kill
be-
it now. We can't run it.
We're looking for a place to dig a fault trench. We study earthquake history. A backhoe comes in, digs across the scarp, and we map all the layers. We try to collect carbon-14 samples or other samples for age data, and we look for when was the last earthquake, when was the earthquake before that, when was the earthquake before that.
So these do occur repeatedly.
They occur repeatedly.
And these particular locations are more susceptible than others to them because they're where the stresses are most likely to release themselves.
No, but they are the best places to record the evidence. So the earthquake breaks the whole fault, but if we don't have a datable deposit, we don't know when that earthquake was.
And there's plenty of verdure here, and
Right. And so what happens when the
carbon-
the earthquake raises that side over there where the land goes up, a little like a landslides or colluvium, just debris from the earthquake. You get a really sharp bank, and then that earthquake or that soil slumps down into the pond here.
Right.
And then if that pond dries out so that we can actually access it, then we can date those deposits.
And is there a time span between them?
There is. It's on the order of 1,000 to 3,000 years.
On this
usually.
particular
On this
fault
particular fault. Although we don't know for this strand, but the work we did further east says the last earthquake was 1,000 years. The earthquake before that was about 3,000 years. The earthquake before that was about 5,000
So what do you
years.
suspect is going to turn out when you...
Something similar to that.
Something similar.
Yeah.
Is there any way we can kind of like get a map of all the tension and stresses that exist? Like you were saying, California runs into Oregon, Oregon runs into Washington. It's a huge, massive, slow train wreck. Is there any way to kind of like get a sense of how much pressure is occurring in all these different locations?
So there is, and we have a technology called continuous GPS where they install a GPS station every few tens of kilometers and it stays there permanently. So every second it's collecting data. So it knows where it is within less than a millimeter precision. And so we can watch those GPS stations as the Juan de Fuca plate is coming in. Those GPS stations are moving with it towards the northeast.
So there's like a drift in all these stations.
Right, and then when the earthquake happens, all of a sudden, so slowly they move this way, and then quickly they
Okay,
move
so
back that
do
way.
they tend to kind of like drift towards each other? Do they drift
Some
in
of
the
them
same
drift.
direction?
Some of them drift towards each other,
Yeah.
and some of them drift away from each other. But on average, most of them are going towards the northeast
Okay. Wow.
until the next earthquake.
And then there'd be a huge jump in all their locations.
Yeah.
And then at the same time, you'll have seismology data about how much energy was released.
Exactly.
Okay.
Exactly. And so and as it's moving to the east, it's also bulging up in some places and down in
So you're
others.
getting elevation readings
Right.
too.
And then when the earthquake happens, the parts that went up will go down, and the parts that went down will go up.
Almost like a huge wave dissipating.
It's an elastic wave.
Cody, can you explain where all this energy is coming from that's causing these like moments of stress that are occurring all over the crust?
Right. Well, really, the driver is plate tectonics, so more superficially. So the mantle is convecting, right, and all these plates are sitting on top of it in the lithosphere, and the convection is what causes these plates to move and run into each other and subduct under one another and whatnot.
Well, you know, when I boil a pot of water for tea, there's like a whole lot of heat in the bottom, and then it sets up these bubbles and turbulence zones and everything
Right.
else. So where's the heat coming from that causes this stuff to boil?
So the source for the heat in our planet comes from two sources. One being just residual heat from the formation of the Earth. So when you had all these different parts accreting to form one planet, that causes a lot of heat, and so there's still residual heat from that 4.6 billion years ago.
Okay.
But there's continuously heat being built from radioactive decay farther down in the Earth's mantle as well. And so that's like the sun. That's where the heat from the sun comes from.
I understand it's as hot at the core of the Earth as the surface of the sun, about 6,000 degrees. Is that correct?
I'm not.
I don't know
yeah.
about that. Yeah.
It's from my astronomy background, that's all.
But
Yeah.
so the heat is generated in the earth, but it's escaping upward. So that's why you think of it like a pot that's
Yeah.
hot.
Boiling.
That's
Right.
boiling, yeah. We're going to look at this bedrock, which is the rock that's attached to the earth, not instead of transported, to see if there's evidence for faulting. And Cody's going to measure some of these things we call fault striations, which are evidence of slipping of one rock past another.
We've noticed that before. Also, we've
Yeah.
noticed like
They're called-
strata in the rock too, where there's different
These
deposition
are called
layers.
slicken sides or slicken lines. And you can see that they're kind of horizontal, kind of scratches.
yes.
Yeah.
Wow.
Scratches and grooves and
She didn't quite start. Go ahead.
okay. This rock is a marine sandstone that's probably around 25 or so million years old. I don't know the exact age. When there was this area was still covered by the sea before the
At
Olympics.
that time, in fact, Antarctica didn't have any ice on it. Snow. 25
That's right.
million years ago.
Right. So what Cody's doing is measuring the orientation
Uh-huh.
and also the angle of tilt of the plane that's on, and then he'll also measure the orientation of the striations on it. You see these grooves here?
Mm-hmm.
So there was another rock here
It slid past it.
that slid past it. And so we know it didn't move up or down. We knew
Right.
it moved either this way or that way. And it looks smoother going this way, like it's kind of almost like a nap.
Uh-huh.
So it probably moved this way.
That direction. So it slipped right past it,
Yeah.
and then later on, something fell away.
Well, this probably fell away.
This probably fell
Yeah.
away, and then it exposed these striations, and it's slightly, like maybe a 15-degree
Yeah,
angle.
Yeah. And we call this left lateral.
Left lateral, because
Because
the
it-
downside is right, so it must have slipped down.
Well, yeah,
Okay.
so it's more sideways than it is up and down. But if you're standing here looking down on top of it,
Uh-huh.
this block moved to the left, this block
Okay.
moved to the
Oh.
right. But if I turn around and look this way,
Right.
this block moved to the left.
Got it.
So
And can you,
conglomerate is a cemented gravel. So the water moved fast enough to carry pebbles right here and only sand grains right here. So there's some kind of layering to the rock. I don't know if you can see this here. It's finer grain here and coarser grain there.
and what she means by conglomerate, I think, is you notice there's a rock missing here that was it was included in this stone at one time. There's a whole bunch of rocks here.
You can look at this
Yeah, they're pebbles
boulder down here. and you
Yeah.
can see
encased
sure.
in sand.
Okay.
But then
So it
hardened.
re-solidified again.
Yep. With a north direction, and the fault that we're studying is more of a northwest direction. So this is probably something much older.
Which goes back past the 1,000 or 2 or 3 or...
Yeah, we don't know how old. It could be tens of thousands of years old. It could even be millions of years old.
Wow, okay. There you go. Beautiful out there.
I don't know if I walked here or somebody else walked here.
Yeah, that's what it looks like it's here too. Yeah, there's tons of berries.
Are there berries?
Yeah.
So there's buried stumps, so be careful when you're walking. This is a great spot to dig a backhoe trench because it's close to the road. The backhoe can just dig a trench perpendicular to this scarp. And what we're looking for is, in each earthquake, this side probably went up and over, and then there would be like a nice fresh dirt face that then would slough down into the trench here, and we would hopefully be able to date those deposits.
And you'd be able to visually look at it and tell that there had been an earthquake instance for each of those
Exactly.
sloughs.
It's called a colluvial wedge. It's kind of a wedge-shaped deposit that comes from here and pinches out that way, and it's coarse debris. It's like a little landslide.
Huh.
Yeah. We want to know, what is this material? Is it glacial? Is it colluvial, which is just hill slope deposits? Is it bedrock?
How deep will you dig?
Not very. The backhoe will dig a lot deeper. The backhoe will dig about 2 meters deep, like 6 feet.
Big, large angular glass. in there.
Yeah. So this whole area was overridden by glaciers, so we expect to find glacial till.
How would you describe till? How would you determine what it was? Is it stones?
It's stones in a kind of a clay matrix, and usually it's harder than this. This is probably younger than glacier, because if the ice was on top of it, it compacts it really hard.
Okay, so that would take you back 12,000 years ago.
Right, exactly.
So if you were to find something here now, what might you say? So, hey, wow, there was a quake here 1,000 years ago. What might you see down there when you're digging at it?
We'd look for some charcoal or some plant material. Like in this little swamp here, if this was ever a swamp, we might find some little fossil leaves, for example. And they wouldn't be fossilized, they'd just be leaves, and we could date them. If we were lucky, we'd find some ash from an eruption, but we're kind of on the wrong side of the volcanoes for that.
So basically, you're assessing this site to determine whether or not it's worthwhile to bring a backhoe here. What might you find today that would say to you, wow, we really got to get the backhoe out here? What might you find?
Well, one thing we've already found, which is the topography. So this is a favorable site to collect sediment, and since it's wet sometimes of the year, maybe it has a little pond, which would collect organic material, which would be good for dating.
Dating.
Yeah.
And also the proximity to the road is nice because you don't want to have to clear a road for the backhoe to get here. It can, and they're pretty versatile. They can come down this slope pretty easily, I would imagine.
I'm walking with Cody up to the top of this upthrust, and he's going to describe the lay of the land because this has a lot to do with his master's project, and he's going to explain that. But apparently, this whole rise here, from what I am understanding, basically came about because of upthrust. So ordinarily, this terrain would be as low as the lower points down below. Is that correct, Cody?
That is correct.
Wow. So I'm looking off over here, over your shoulder,
Yeah.
and I can see it's probably at least 15 to 20 feet lower down there.
Yeah, so you can see that this is truly a ridge. You can think of it where you have a steep side behind you, and over here it gently slopes back down. So this side here is actually where the fault is. So you would imagine when this came up.
Sure. So this whole rise here
Yeah.
is actually an upthrust from an earthquake activity.
Right, and you can see that it extends. Here, I'll go.
He's going to give a stump speech on geology. Here we go,
You
Cody.
can see that the ridge extends this way,
Uh-huh.
both the west and the east. And And when we look at this on the LIDAR map, we can see that this ridge continues for several miles in both directions. So because this fault is so extensive, one of the questions that we want to answer, or one of the questions that we want to ask first, is how does what's called the slip vary across the fault, and also the slip rate. So the slip being is the amount that the earthquake displaces along the fault. And what we could do is measure it first of all. So how much does it go up and how much does it go laterally on the west side of the fault versus, or the east side of the fault versus the west side of the fault. And we want to see if there's any kind of gradient or if it's continuous across. And additionally, if we can get some good age data to go along with that slip data, we can calculate rates and compare, does it slip faster on this side versus slipping faster on that side.
Okay, Cody, based on the data you collect on this east-west fault line and the dates associated with them, ultimately, hopefully you'll get, what kind of conclusions about the future do you think you're going to be able to make?
Right, well, so a lot of this is determining which parts of the fault might be more active than another part of the fault. So if we see larger amounts of slip and higher slip rates, say further to the on this side, then we can say that likely an earthquake might happen over here versus over here. Or counter to that too, we could say that this side hasn't, if this side's been more active recently, potentially over here, you could think of it as this side's being due for an earthquake because it hasn't slipped.
And in terms of time scales, you would be thinking hundreds of years?
Around thousands of years.
Thousands of years.
Yeah, Liz did a study further that way, and that was the interval that they calculated from that. So that's another question. We're going to see if this has slipped more recently, and also is the slip rate consistent between the west side of the fault and the east side of the fault.
I see there's some beautiful mountains off in the distance there, Cody.
Yeah, so the mountains that you see in this area are all related to the deformation that's happened over millions of years in this region.
So the time scales on the mountains, which are huge, were millions of years. Is there any chance that this could eventually become a mountain?
Eventually, if this fault does remain active. These faults are more strike-slip faults, meaning that the movement is more like two plates rubbing against each other rather than an uplift happening.
Okay.
So farther into the core of the Olympic Mountains is you have more dip-slip faults.
Dip and slip.
Meaning that there's more vertical displacement rather than horizontal displacement like there is here.
Okay, so...
and so that is great for building mountains.
and this is good for building hills, would you say?
Sure, yeah. Like if you look at the San Andreas Fault in California, for example, along it you do have small mountains that are formed by this strike-slip fault, which is the San Andreas Fault. But it does, over large times, like geologic time, does form pretty impressive topography like mountains that you see here.
Yeah, we got lots of information. We had a great overview of the difference between the kind of fault activity that results in mountains like in the distance and the hills that this might become in the future. And do you have any last words you want to share, Liz, before we wander off and you guys actually have to start perspiring a little bit?
No, just thanks for coming and being interested in our work.
It's brilliant.
Be prepared for the next earthquake.
Not in Arizona. If we experience one, it's going to be somewhere up here.
Yeah, that's right.
So, on when the next earthquake is? Could be.
There'll certainly be an earthquake in sort of 30 to 50 years, because the one like the 2001 in Nisqually earthquake,
Right.
those happen about every 30 to 50 years. Those are in the deep slab beneath Puget Sound. The ones that are on these kind of faults are more like every 1,000 years, and the ones offshore, the big tsunami-inducing ones, are about every 300 to 500 years. So the deep ones are more frequent, but they're deep, so they're not as damaging.
Wow, so catch the wave.
Catch the wave.